Okay. Alright, unfortunately I'm not going to be in class today because I have a sick son. But I'm going to take you real quick through the notes. We're going to be talking today about the normal force and angled forces. So what happens when things are pulled at an angle and how you analyze the forces. So this unit is going to deal with angled forces first, and then we're going to look at forces in an elevator, and then we're going to look at forces with an Atwood machine. But today is just going to be angled forces. Okay, and so we're going to look at situations, all unit with different applications of Newton's laws and setting up free body diagrams and all that. So this unit is just called Newton's laws application. Now, one thing is we are trying something new this unit. We are going to, it's a packet unit. So you should have a packet that's got all the notes right there with the notes problems. So you should have that packet in front of you right now. Make sure you have it before we move on. Alright, so first one. If you look over at your notes packet, you'll see the stuff about the normal force. So we've always talked about normal force being equal to the weight, but that's not always the case. So on the first example, it says a 10 kilogram box sitting on a table. Draw a free body diagram with the normal force. Well, if the box is just sitting there, then the free body diagram is, normal force up, weight down, and then you can easily determine that the weight equals the normal force. So this is how we've been doing it. But what if someone pushes down on the box? So it's an extra force. So on your next one, it says someone pushes down. So you have your free body diagram. And instead of just the weight down, you also have an applied force. This is that person pushing down. And then the normal force is up. Remember, the normal force is basically how much force the surface is applying back on the object. So if the object already weighs a certain amount and you're pushing down on it, the normal force is going to have to be all of that force. And since the net force is 0 on this book, it's not accelerating, the forces are balanced. So the normal force has to equal the weight plus the applied force. And so that would be 100 newtons that we already knew plus 30 newtons. So the normal force is 130 newtons. Alright, but now if you pull up with 30 newtons, instead of pushing down like we did here, if you pull up, the applied force just goes up here. The applied force goes on the top of the diagram now. You still have weight at the bottom. And so the normal force is, the forces up equal the forces down because all the forces are balanced. So the normal force plus the applied force equals the weight. So the normal force is the weight minus the applied force. And it's 70 newtons. So basically, since you're already pulling up on it, you now have the normal force will be lower than the weight. Alright. So now we're going to look, you can go through this review example yourself. Also, I post this PowerPoint on the Schoology and it has all this stuff. I just wanted to narrate it real quick so that you could kind of get ready and have somebody narrating the problems for you. So in a review example, you're doing just the normal one. So we're going to look at, it's just the force is applied and it's not at an angle. I think yours has a coefficient of friction. Go ahead and cross that out. I think it has a coefficient of friction like 0.8. Cross that out. You don't need that because it's moving at a constant speed. So at constant speed, the weight is 30 newtons. The force is not being applied at an angle, so the normal force is also 30 newtons. And then the frictional force, or the applied force, is 24 newtons. So the frictional force has to be 24 newtons because it's being moving at a constant speed. So all the forces are balanced. So applied force equals frictional force. Alright, but we're going to look at angled forces. And if you look at angled forces, instead of pulling perfectly perpendicular, we're going to pull at an angle. And so the angled forces are always going to have some angle associated with them, and you always have to find the components of these forces. So there's always an x component and always a y component. The x component is always whatever the force is. Okay, so if this was 100, whatever this force is, the force being applied at an angle, multiplied by the cosine of the angle, assuming the angle's right here, which we always put it there. So here I assume the angle's right here. And then the y component is the sine of the angle, or is the F, the force applied multiplied by the sine of the angle. So you can't do anything with angled forces, so you've got to break them up into components every time. And that's what we're going to be doing on this next problem. So now, everything's the same as the other problem, the review example, but we're going to put the force at an angle. Okay, and I have screenshots of how to work this problem. So you start by drawing the free body diagram, and remember, if you need to pause the video, have the sub pause the video if y'all need to catch up. So we're going to draw the free body diagram, find the block's weight, find the normal force, and find the kinetic friction force. Important to note that it says everything's the same, so we're going to assume it's moving at a constant speed. Okay, and you can take out, I think yours gives a coefficient of friction of like 0.8. Just take that out. Act like it's not there. Alright. So, this is the free body diagram. Normal force up, weight down, friction to the left against the direction of motion. And here's the angled force. It says it's a 24 Newton force. So I drew the angled force here and then drew the components. So you have to find those components. So on the first one I actually did the trig, show you why the x component actually uses cosine. And then on the next one, you can see the one for sine. So it's the force, so 24 newtons multiplied by the cosine of the angle gives you the x component of the force. And then 24 times the sine of the angle gives you the y component of the force. So instead of 24 newtons at an angle, you now know that that force has an x component of 20.78 newtons to the right. And I changed this from left to right because I like everything going right. So it doesn't really matter either way. And then the y component is 12 newtons up. So what I do is I redraw the diagram. So when you redraw the diagram, instead of the angled force, I put the y component of the force here, the x component of the force here, a lot easier to look at. Also, we know that all the forces are balanced because it says moving at constant speed. So to find the normal force, you know the net force has to be 0, so all the up forces have to equal the down forces. Okay, we can ignore these right now. So that means normal force plus the y component of the applied force has to equal the weight. Okay, and then if you write that down, the normal force has to be the weight minus the y component of the applied force. 30 minus 12 gives you 18 newtons. Okay, so that's the normal force. All right, and then finding friction is easy because it's moving at a constant speed. All the forces to the right have to equal the forces to the left because everything's balanced. So whatever you got for the x component of the force has to be friction, and we got 20.78 for the x component of the force. All right, remember you can pause the video anytime. All right, so on to the next one. On this one, we're going to actually have to find an acceleration and a net force, so not moving at a constant speed. So you notice I gave you a mu here. Okay. And what this does, this tells you the coefficient of friction between the surface and the box is 0.3. So we're going to do the same thing. This is the diagram. Okay, but you want to break it up into components. So instead of having this angled box here, find the components. So it was 60 newtons at a 30-degree angle. The x component is 60 times the cosine of 30. The y component is 60 times the sine of 30. You get 52 for the x, 30 for the y. And then redraw the diagram. Instead of having the angled force on it, instead of having this angled force, have the two components that make it up. Makes the diagram a lot easier to look at. Now we know that the top and bottom forces are always balanced. Okay, but this time the x component and the friction will not be balanced, and that's what we're going to have to figure out. So first, find the normal force. The forces up has to equal the forces down. So if you look, you have N plus the y component of the force has to equal the weight. If the top and bottom forces are balanced, then these two combined have to equal the weight. So the normal force is the weight minus the y component, and it's 100 minus 30. Now if you think about it, it makes sense. This has got an upward angled force. So that means you're pulling some of the weight, some of this 100 newtons is being relieved because you are pulling up on it a little bit. So then it makes sense that the surface doesn't have to push back with the full 100 newtons. So it doesn't have to totally balance the weight because you're pulling up a little bit. And that little bit is 30 newtons. You're pulling up at 30 newtons. So that takes that force that the surface would have to apply back. Take some of that off. So that's 70 newtons. And then to find the frictional force, remember frictional force is the coefficient multiplied by the normal force. So 0.3 multiplied by 70 newtons gives you 21 newtons. And then you can plug that in. So the 21 newtons would go here. The x component was 52 newtons. That was from the other slide. Remember the x component was 52 newtons. So the net force is just what is the imbalance of these. So 52 minus 21 gives you 31 newtons. And then of course the acceleration is just the net force over the mass. The mass was 10 kilograms. So it's 31 divided by 10. So it's 3.1 meters per second squared. And again, you can pause the video at any time. Now, if you look, this is this is everything filled in. You've got the normal force of 70 newtons. This is back to your original picture. The frictional force of 21. The weight is 100 newtons, and then the net force was 31 newtons, and the acceleration was 3.1 meters per second. All right, so I want you to work out problem number 1 and 3 on your homework sheet, and show your work on separate sheets of paper. Now, it's up to you. You can work them in your notebook like you've been working them, and then tear the paper out. We're just trying something new here. See if you guys like the packet units better. See if that helps. And if not, then we'll look at something else. Now on the next slide, I'm not going to go to it because I didn't put it up yet. But on the next slide, there's a link to the physics classroom that has a tutorial on this same stuff. So it's just written out. And there are people doing it, but it's not a video, it's just written out. And so if you want to go to that, it'll be on the next slide. This PowerPoint is going to be in your Schoology account. If you go to the folder that says Applications of Forces, then you'll see this video. Alright, have a good one. Be good for the sub.